Over the last year, we've seen multiple transformer models being proposed to solve image registration problems. A claim that's often made is that transformers are inherently better at registering long-range displacements. However, this claim is never validated in these papers. In this work, we actually look at this claim and compare how transformers stack up against CNNs on long-range displacements. In deformable image registration, we want to register a pair of images. In our work, we look at lung images, and here we have an example of a red lung and a green lung being overlaid. And we want to register this red lung to the green lung. That means for each point in the red lung image, we are looking for its corresponding point in the green lung and mark this displacement by a displacement vector as annotated here. These displacements can get pretty long. So on an isometric grid on a lung image, we are looking often at displacements of more than 50 pixels in the extreme regions of the image. In the old times, we used convolutional neural networks to solve this task. CNNs are quite accurate at solving image registration, and compared to methods we used before we tackled this problem with deep learning, they are also incredibly fast. However, there are some questions about how suitable convolutions are for image registration. Convolutions have no inherent capability to perform the spatial matching of image components that is required to solve the image registration problem. And convolutions are also an inherently local operation that only looks at the local neighborhood, raising questions about how capable CNNs are at finding these longer range dependencies. Now, over the last year, we've seen a new model architecture being proposed to solve this problem. These are transformer models. And on the surface, transformers look like a quite good network architecture for registration. With the attention mechanism, there is an inherent inbuilt capability to perform this matching of different image components that we need for image registration. And if we use the global attention mechanism, there's also no assumption on locality. So we can look for matching parts all over the images. And transformers have also performed really well on registration tasks. On the learn-to-reg brain registration task, transformers currently hold the top 2 spots, and they outperform CNNs by a fair margin on these benchmarks. One common claim you often see in these transformer papers is that transformers are inherently better at capturing long-range relations in the images. So in the introductions of these papers, we read phrases such as that transformers are better for capturing long-range spatial information, they learn long-range spatial relations, or transformers have an inherent capability for structured data processing. But these claims are sadly never validated in these papers. So we designed an experiment to put them to the test. We use 3 registration models. One is voxomorph, a quite popular UNet-based approach, and we stack it up against 2 transformers, one based on a vision transformer and one based on a shifted window transformer. And we evaluate these 3 registration models on the registration of lung CT images. In these lung images, we have displacement vectors annotated as ground truth, and we can evaluate registration performance based on how long these displacements are. And when we plot this, we have the ground truth displacement length on the x-axis here and the registration error on the y-axis. We have the 2 transformer models in red and blue, and we have the UNet-based approach in green. We see that overall the transformers do perform better than the UNet, but if you look at the small displacements, here we also clearly see that the transformers outperform the UNet quite strongly. But if you look at the longer range displacements where this claim is made, we actually see the opposite is true. Here, the UNet actually outperforms the transformers for the extremely long displacements. So in summary, we observed that yes, overall transformers do outperform CNNs. However, this performance comes mostly from the small displacements and not, like previously thought, from the longer displacements.